This course called Mathematical Thinking is something that my colleague Amritanshu Prasad at IMS and I have jointly taught. And the thing we tried to do there was sort of try to give some samples in some sense of how proofs and mathematical formulations, mathematical thinking in general works. So my plan for today is more or less the same thing. I'm just going to pick up some very interesting, or what I think are very interesting snippets, bits from the broad area of permutations, and try to, let's explore and see if we can understand it from many different ways. So that's broadly my plan for today. By the way, feel free to interrupt anytime if anything I'm saying is not very clear and so on. So for me, the starting point is going to be permutations. So I imagine everyone sort of encountered permutations before. So let's write out a few examples. So if you have three objects or three numbers, 1, 2, and 3, then here's the full list of permutations. We could just write them out in the usual order, or we could say interchange the first two. We could interchange the last two. We could interchange the first guy and the third guy, so it becomes 3 and 1. Or we could sort of move them cyclically. So 3 comes to the beginning, 1 goes here and 2 goes there. Or we could push it cyclically in the opposite direction. So in which 2 comes here, 3 goes here, and 1 sort of moves cyclically to also, right? So I've just written out all possible ways of arranging the numbers 1, 2, and 3. And there are only 6 ways of doing it. Right? So these are what we call the 6 permutations of 1, 2, and 3. Now in general, how many ways are there of permuting 4 numbers, for example? There will be what? 4 factorial, right. So which is 24. So if you take n numbers in general, so if I've got, say, let's maybe write them out in usual order. I have 1, 2, 3 till n, then as you know, the number of ways of writing them out, permuting them in all possible ways, is what you call n factorial. So this is the total number of permutations of the numbers 1 through n. And I mean, it's not too hard to see why this works. But so here's a question: where do permutations occur, or where have you encountered permutations? In what contexts? Other than, of course, in math itself, when we study arrangement of objects. Okay, so in what other fields is sort of what I'm maybe curious about. What? Grouping students. Okay. Right? So if you actually want to solve real life problems like that, where you actually have people or arranging objects, agreed? Huh? Programming? Where in programming? Right. Right. So for example, when you write algorithms to manipulate things like, I don't know, trees, or when you, or what else? Sorting, for example, right? When you write algorithms to sort, in a sense, what you're doing is really working with permutations in some way, right? Sorting is like saying, I have a permutation, things are in mixed up order, and I need to find some way of putting them back in the correct order. So that's sorting. Any other disciplines in which you may have heard of? Creating class timetable, right? So that's more like, I think, real life applications in some sense, correct? Investing. Yeah, where? I don't know. I'm curious too. Yeah. Right. Okay. Fine. So in some sense, you're looking at the same thing of, I have some objects and you're trying to see if you can agree. Someone said something else. Probability, correct, sure, it occurs a lot in probability. Strangely, it occurs in physics. I don't know if you have, anyone encountered any physics before? Do you know where these occur in physics, permutations? So quantum mechanics, surprisingly, which is sort of supposed to be the theory which tells us how very, very small particles behave, for example, right? So when you have n identical particles, for example, when you have say n electrons, and when physicists try to write out what they call the wave function of that system of n electrons, then what naturally comes up is permutations. So they take the wave function of a single electron, and then they kind of take n such things, and then they have to permute them in all such ways. So I don't know, in school you probably have studied things like Pauli's exclusion principle and so on, right? Which says that, I don't know, anyone remember what Pauli's exclusion principle is? Me neither, actually. Right. So in a sense, what it says is that in an orbital, or we draw those boxes, right? You cannot have, in a sense, two electrons both with the same up spin, for instance, right? Or in other words, it says that with any given state, that is, you say, okay, it's in the third orbital, 3, whatever, s or p, right? If you fix the number, if you fix the orbital, then, and you fix the spin also, you say, okay, I want up spin, then there can only be one electron which has all these properties. There can only be one electron in any given state. So it's Pauli's exclusion, because he says it's excluded. You cannot put a second guy which has exactly the same properties as the first one. So this property actually comes in quantum mechanics by applying a certain permutation operation and so on. Okay, so I won't get too much into this, but sorting is maybe the most the thing which one encounters the most, especially since you guys are looking at data science and various computing algorithms and so on. Okay, so what is my goal for today a little bit is to draw pictures. Okay, so I mean, this is of course a nice mathematical concept, but a lot of this, it turns out, can actually be understood with pictures. Okay, and they're going to be pictures of very different kinds. There are many different types of pictures that we'll draw for the same thing. Okay, we'll try to understand this from many perspectives. So the first picture, so my first question is this: if I give you a permutation, right? I give you somebody, I give you, I don't know, let's take this fellow, 1, 3, 2, and I say, okay, your job is to draw a picture which represents this permutation. What sort of picture would you draw? No, you're not allowed to use any numbers, nothing. Triangle, why? Huh? There are 3 numbers, then, but how would, if I give you this guy, what would you do? Would you also draw a triangle? So I agree, if you draw a triangle, then maybe somehow it says there are 3 things, but I also want a picture for this fellow and for this fellow and I want a picture for every permutation. So you cannot draw the same picture and give me, right? Then I will not know whether you are talking about this guy or that guy. Any? No, but why is that the permutation? So let's do 1, 3, 2. So I want the permutation 1, 3, 2, and I want a picture for 1, 3, 2. This is represented by some picture. So if you just draw, huh? Oh, acha, you're saying you will draw 1 and then 3 and then 2 apples, like that. I see what you mean. Okay. Okay, fair enough. Yeah. Huh? Circular, just a circle you mean? Okay. But why, how would that circle tell me it is 1, 3, 2? No, but I'm not allowing you to write any numbers on the circle. Huh? Dots, so sort of like apples, like you said, right? Draw 1 dot, 3 dots, 2 dots. Okay? But I'm going to use lines to draw this permutation. Okay? So let me draw my pictures and then maybe you can tell me what I mean by my drawing. So I'll draw my pictures in the same order. So I'll start with 1, 2, 3. Okay, so now I have 2 and 3. That's the second guy. Let's draw the next fellow. 1, 3, 2. Okay, so I should tell you what is each. So this fellow is 1, 2, 3. Let's draw the next fellow. 3, 2, 1. So that is okay. Let's draw the last two. 3, 1, 2. So this is 3, 1, 2 and 2, 3, 1. Okay, so I've drawn some 6 pictures and I claim that these 6 pictures represent my 6 permutations in some way. So how am I drawing my pictures? Huh? What? Okay. Okay, correct. Okay, sounds good. So let me then ask you, suppose I tell you 4, 2, 1, 3. I now give you a permutation of 4 numbers. Now I need you to use what you said to draw me a picture of this. How would you do it? No, you have absolutely the right idea. So, which is that somehow when things are out of order, there is some intersection. So, as she said, see 1 and 2 here. So, I mean 1 and 2 are out of order. So, imagine that there is one line. See, there are always 3 lines, right? The number of lines is always 3. So, maybe the best way to think about it is imagine that there's a number. I know I told you I'm not allowing you to write numbers, but suppose I did do that for a second. So in all these figures, I'm going to write the numbers 1, 2 and 3 like this. You know, in the same order, 1, 2, 3, 1, 2, 3 on all sides. Imagine for the moment you had these numbers. Now can you see how the permutations are so 1, 2, 3 says in the first position I have a 1, right? So what we often do is this. See, if I give you a permutation, so let's start with 1, 3, 2 for example, like we did 1, 3, 2. That's my permutation. We sort of attach to it the position number. So this is the first position. This is the second position. This is the third position, right? There are 3 positions in your permutation. Is this fine? So I have just added some extra information on top. I'm also keeping track of the position numbers. So now I think of a permutation as follows. Not as I have some n things and I move them around. Instead, think of it as there are some position numbers. Each position number you must fill one of these numbers. So in the first position, there is a 1. In the second position, there is a 3. The third position, there is a 2. That's what 1, 3, 2 is. Right? So here's 1, 3, 2. Think of this as a position number. First position, second position, third position. So I'm putting them in blue. And these lines are just telling me what they map to. So 1, in the first position, I have a 1. The second position, I have a 3, so I connect the 2 with the 3. In the third position, I have a 2, so I connect the 3 with the 2. Is all right? Is it clear how I drew these diagrams now? So let's just test our understanding by seeing if we know how to draw the diagram of this guy. 4, 2, 1, 3. Okay? Maybe you guys should try for a second and then we'll see if we get the same answer. So just for ease of this, let me put the dots corresponding to the positions. So there are 4 positions, 1, 2, 3, 4. And there are 4 possible entries. And I have to figure out how to connect them. Okay? So where do I connect this first blue dot? to the fourth guy, because in the first position I have 4. It's 4. The second position I have a 2. So connects to the second dot. Third position is a 1. Okay. So I should connect this fellow to that fellow. So I'll do that. And the last guy is a 3. So the fourth position, this fellow is a 3. Fine. So what I did is I drew a picture, and this picture tells me, this picture represents this permutation for me, right? It's 4, 2, 1. Okay, great. So let's now come to this very nice insight that you had about this, that somehow crossings are important. So why would you draw a picture firstly? Usually when you draw a picture, there is something that you can get out of the picture which you couldn't have gotten by just staring at that list of numbers, right? The picture often conveys more. That's the hope. So here, this picture conveys something which you couldn't have gotten out of this, at least not so easily, which is the following. There is this intuitive notion of a crossing, 2 lines cross. So let's see, where are all the crossings? How many crossings do we have? 1, 2, 3, 4. So this permutation diagram has 4 crossings, right? Now, what did that tell us about the original permutation? What does a crossing actually mean in terms of the original permutation? They are out of order somehow, right? Huh? No, none of them is in its position may not be true. In this case, 2 is in its position. 2 is actually where it should be, right? 2 did not move, the others moved. But what it is saying, it is telling you something about pairs of entries. It's saying 2 things are out of order. Okay, let's see what we mean by that. So let's look at each of them in turn. So let's look at this first crossing here. Okay, what was this crossing? So let's draw. So this was position number 1, and this line is the line which connects 2, right? So this is the line which connects 1 with 4 and the line which connects 2 with 2, right? So this crossing is actually for the position numbers 1 and 2. Okay, so what it's saying is, if you look at the entries in position numbers 1 and 2, okay, what are those entries? They are 4 and 2, so they're out of order. See, what is the ideal thing? You expect that permutation means, what is the best, most well-behaved permutation? It is just 1, 2, 3, 4. Everything written in ascending order. Nothing is out of order, right? That's the most well-behaved permutation in some sense. But now, this guy, in the first 2 entries, there is something out of order. It's now 4 and 2. Okay, it has become in descending order instead of ascending. So that when that happens, you will see a crossing there. Okay, let's look at another crossing. This fellow here. So what does this crossing correspond to? So let's see which 2 lines are intersecting. 3 going to 1. Right? So this crossing I have taken care of. Let me look at this fellow now. This is the line 1 going to 4 and 3 going to 1. Right? So this is the crossing which corresponds to position numbers 1 and 3. Right? So let's look at the entries in positions 1 and 3, which is 4 and 1. Again, they are in descending order. Right? 4 is bigger than 1. So somehow they are out of order. Right? So a crossing just says that pair of entries is out of order. So let's see, the same works for all of them. So let's look at the next crossing, this fellow, which connects to position numbers 2 and 3. So 2 and 3 are the numbers 2 and 1. Again, they are out of order. They are in descending order. Finally, last crossing between 4. This is 4 and 1, right? Position numbers 4 and 1. So that's 4 and 3. Those are the 2 entries. Again, they are out of order, right? No, what do you mean ascending order but still out of order? No. If they are in ascending order, they will not intersect. For example, let's look at these 2 guys. Okay, so 2 and 3 is in ascending order, right? So let's see what happened to their lines. Okay, where are their lines? The line corresponding to 2 is this fellow. Right? Position number 2, 2 going to 2. The line corresponding to this guy, position number 3 is 4, 4. For a second I got scared. So 4. So you see those two lines did not intersect, right? So they will not intersect if the corresponding entries are in ascending order, and they will intersect when they are in descending order. So this intersection correctly captures that particular aspect. That pair of entries is now in descending order in the permutation. Okay? So this thing, you know, a pair being in descending order has a name. We call it an inversion, which is sort of what the English word means. It's an inversion. They are inverted. In some sense, they are in the wrong order. Okay? So this sort of a pair which is out of order of a pair of entries which is in descending order is called an inversion pair, if you wish, or just called an inversion. It's called an inversion of that permutation. Okay? And what crossings count is the total number of inversions in a permutation. So that is what crossings finally end up calculating. Okay? So let's see if we understand this notion of inversion correctly. Suppose I have the numbers 1, 2, 3 and 4. Okay? So let's see if we understand what are all the permutations which have 0 inversions. I want a permutation, I want all of them, in fact, I want many if there are there, of permutations which have no inversions at all. Firstly, what should the diagram look like before we even worry about what the permutations? Four, right? I said there should be 4 lines. This is the only possibility. Can you think of anything else which will not have intersections? Which will not have inversions? See, if this line 1 from the first position, it goes to anything else, 2, 3 or 4, then something from somewhere will have to go to 1, right? So these two will end up intersecting. So 1 has to go to 1, 2 has to go to 2 and so on. So there's only one guy which has no inversions. And what's that corresponding permutation? First position is 1, second position is 2, third position 3, fourth position 4. So this is just our well-behaved permutation. Everybody is already in ascending order, right? Nothing to do. That guy is the only one which will have no inversions. Every other permutation will have at least one inversion. Okay? Now let's ask the complementary question with again same thing, 4 numbers. Can you find the permutation which has the largest number of inversions possible? What do you mean by opposite? Right. So we just have to write this in descending order now, right? So how do we get as many inversions as possible? You just put everybody in the wrong order. That's the idea, right? So let's look at 4, 3, 2, 1. And how many inversions will it have? 4, 6, why? Let's draw and check. So take the permutation 4, 3, 2, 1. So let me draw it. This 1 goes to 4, bottommost guy. 2 goes to 3. 3 has to go to 2. Okay. Now there is a slight thing to keep in mind while making these drawings, which is the following, that see I didn't quite say what rules I'm using to draw my lines. So I said I want straight lines, but of course if you strictly follow that to the letter, the trouble sometimes may be that when you try to draw, depending on where you placed your points, see when I draw that straight line, it may actually pass through this point itself. Right? If you insist on drawing everything as a straight line, joining one to the other. So let me complete. So then this 4th guy, maybe it also passes through this. It's possible, right? If I correctly take equally spaced lines and I draw only straight lines joining everybody to everybody, they'll all pass through the same point. So now the question is, how many crossings are there? It's not clear how, right? Firstly we have to understand what is a crossing. What do we mean by a crossing? So crossing is, it's not just the point that I want to know. If, it's also two lines crossing. So if I say how many crossings are there, I can say, see, this white line and blue line are crossing at that point. So that is one crossing. Then maybe if this guy is green, then I can say white line and green line, that counts as a crossing for that. Green line and blue line, they are crossing, and so on, right? So, but we often don't want to have this confusion happening. So what we will do, we will agree that when we draw our lines, let's not be very militant about drawing straight lines only. We'll allow for some curves. The idea being, we don't want these sorts of multiple intersections. I don't want 3 and 4 lines to keep meeting at a point. Whenever that happens, I will just, jiggle my curve a little bit. So I wouldn't draw it like this. Instead, we'll draw it in such a way that all the intersections are separately visible. Okay. So what I mean is this. Let's draw the diagram of this fellow. 1 goes to 4, 2 goes to 3, 3 goes to 2, so I'll just draw it like a curve like that, it's supposed to intersect, and 4 goes to 1, so I'll ensure it intersects every other fellow on its way out, right? So instead of drawing everybody passing through the same point and so on, so I've drawn the same diagram. This is not necessarily to draw straight lines. See, this line is only expressing a relationship. It is only saying that the first position, there is a 4 in it, that's all. But why should I draw a straight line to express that fact, right? So I will draw it like this, but I'm doing this mainly so that instead of everything coming together, I will actually have all 6 intersections separately visible. See this fellow. So I actually can see all six intersections. So there will be 6 intersections, not 4, because every pair of lines intersects, right? And there are 4 lines. So what does one use to? So it's what we call 4C2, right? If you have 4 objects and you want to see how many intersections every pair intersect, it's equal to the number of pairs. The number of pairs is exactly 4C2 or 4 choose 2, which is 6. So you see all the 6 points of intersection in this case, okay? And this will be the only guy for which you will get 6. The maximum number of inversions possible is only 6, right? Okay, so here's the question. Can you manufacture a permutation which has 5 inversions? How will you do this? How will you find something which has? So let's start with 6. We know how to get 6. Can we tweak it a little bit to get something which has 5 inversions? No, I'm not asking for number. I want to know, can you find a permutation which has exactly 5 inversions? Huh? Okay, what did you do? Okay, very good. Switch one pair. Okay, so somehow we must reduce the number of intersections by 1. So we'll do the following. Okay, so this is sometimes called track switching. This is something that you will see, sort of when you have railway tracks and so on, you have this, right? So one track comes like this. There's another railway track which comes like this. Now what you can do is the following. When they come together, you sort of let this train go along that track and you make this train go along this track. Okay, so this is what you sometimes call track switching. So I have these 2 trains which are supposed to come along these tracks, and where they meet, I sort of just, do this little curve thingy. So now, I've kind of changed these lines a little bit. Let's see what happens if I do this operation to this guy. So to start with, this fellow had 6 intersections, 6 inversions. Now I'm going to do my switching operation. So let me do it to the first 2 guys. That is, see, I take the first line. This is the first train, right? There's a train coming down along this track and it's going to reach 4. There's another train starting at this place which is going to go to 3. Okay, so I'll take these 2 trains and I'll switch them. So firstly, where do they intersect? they intersect here. Okay, so I will switch their tracks there. So let this fellow go here. Okay. Now, how many points of intersection do I get in this picture? 5, right? That was my goal. I want to get 5 intersections. What I did was I got that by changing one of these intersection to a non-intersection. I just made them not intersect. Now, what permutation have I manufactured? So it's not 4, 3, 2, 1 anymore. Let's read the tracks. Train starting at 1 will reach which destination? 3. So the first position is a 3 now in this permutation, right? First position is 3, second position is 4. Third, no change. Those 2 guys I didn't touch. 3 goes to 2, 4 goes to 1. Right? The original fellow was 4, 3, 2, 1, remember. That guy, descending order guy, had 6 inversions. This fellow has 5 inversions. And how did I get this? What I did was to switch, right? So someone gave that suggestion of switching. I just picked which 2 to switch, that's all. So I just said, okay, see 4 and 3 are in the wrong order. Let me do track switching. I switched. Basically all that happened here is that these 2 guys got switched. Okay. Now how do you make something with 4 inversions? Let's do one more switch, right? So let's keep going here. So I will again see. So trains 1 and 2 don't intersect anymore. Let me go to the next pair. 2 and 3, do they intersect? Train number 2 goes to 4. Let's just do this. 2 and 3 are intersecting here, so I switch them there. So this fellow only has 4 inversions. And let's see what now happened. I have interchanged 4 with the 2. Right? So now 2 goes to 2, 3 goes to 4. So in position 3, I now have a 2, and here I have a 4. So all I did is just switch these 2 guys. That's what it happened. Now I keep going. Now I'll take train number 3 and 4. They meet here, so I switch them. 3 goes up, this fellow goes here. Okay, now observe that at this point the curves will look rather strange. For instance, 4 is going to 4 now, right? So after doing all this, actually 4 is connected to 4. I could have connected by a straight line, but remember I said I'm going to allow curves as long as I don't get any strange intersections. So now this curve is actually connecting 4 with 4. So you see, it's like an interesting thing. I had lots of tracks to start with, and then whenever they're intersecting, I'm doing this switching operation at those tracks. And if I keep doing this, where will I land up? Huh? I'll get 1, 2, 3, 4 finally, right? So let's do it. So once more, I see track number 1 and 2 are meeting there. So I switch them. Okay. Track number 2 and 3 are again meeting here. So I switch them. 2 goes up, 3 goes here. 3 and 4 are not meeting, so nothing to do. Any more meeting? There's still one more guy. 1 and 2 are meeting. Okay, now let's look at the final output. It's a collection of strange curves, but 1 is connected to 1, 2 is connected to 2, 3 connected to 3, and 4 is connected to 4, right? So if we get back to 1, 2, 3, 4 by this sequence of switching. And if you notice what we did at every step, we kind of just switched. So initially I had 4, 3, 2, 1, then I switched the first 2, then I switched the next 2, these 2 guys, then I switched these 2 guys. Okay, and then again I started from the beginning. I said first 2 guys are again out of order, switch. Next 2 are out of order, switch. No, last 2 are in order. Last guy I switch again, I get this. So what have I done going from here to here? Reduce the number of inversions, but sorting, what algorithm for sorting is this? It's called, I don't know also. There are two of them, right? Exchange sort and bubble sort. I think they are, I don't know which is which. But this is one of them. So this is one of the sorting algorithms, right? So this is one of the standard sorting algorithms. It's either called exchange sort or bubble sort, which is you kind of start by, just comparing adjacent pairs, and, you pass it's a multi-pass algorithm. You have to pass from one end to the other, once, and then start from the beginning again once more, start from the beginning again once more, it's typewriter method. And then at the end of the whole process, you're guaranteed to get back to 1, 2, 3, 4. So what we have done here with track switching is just implemented sorting. So this is how sorting works in general. Okay, good. So this is the reason why we want to draw pictures. I guess that's one of the things I want to say, that by drawing these pictures with lines, we have managed to understand what inversions are, right? What these intersections mean and what role they play in sorting. So that's the first picture. Okay, let me draw a second one. So what I'm going to do is to say, these lines that I drew are all 2D, right? They're just two-dimensional pictures. Now I'm going to draw three-dimensional pictures. Okay, what does a three-dimensional picture mean? So for instance, if I got 3, 2, 1, this permutation, then the picture we would have drawn earlier is this, right? This goes here, 2 goes to 2, this fellow goes to 1. So that would have been my picture so far. But now I'm going to not think of them as just some lines or threads joining these guys, but I will think of them like roads. Okay? So what do I mean by that? My rules for drawing are going to be the following, that I will start with this very first line, okay, which connects 1, 2, 3. So this guy gets highest priority. The first position, the thing which lives in the first position. So I have constructed a road between points 1 and 3. Okay. Now I'll move to the next guy. So I need to construct a road which connects this 2 to a 2. Except, this first fellow has higher priority. So when I try to draw construct the road, I have to decide whether I'm going to whether I'm going to construct a flyover or an underpass at that point. Okay, I have to cross this road somehow. I either cross this road by going above the road or below the road. Okay, now over crossing or an under crossing. Now this fellow has higher priority, so he will go up. Okay, that's the rule. So when I come here and I see a road that's already been constructed, I have to go under it. Okay, so I'll draw this path. So it's 3D. This is what I meant by 3D. So it connects this, but it goes under. Okay, then the next fellow comes and constructs the road. By that time, these two roads are already constructed. So when he finds that he needs to cross this road, he'll have to go under it. Okay, he has to go under any road that he finds. So when I want to connect this 3 to this 1, okay, I either draw it above or below, it doesn't matter. So when I go, and when I come here, I go under. Okay, so which I denote like this, I go under. Again here, I go under. And I join. Is it okay? My drawing is not particularly great. So that's what I mean by a three-dimensional version of the previous diagram. So let's draw one more maybe. 4, 2, 1, 3. I'll start with maybe 4, 3, 2, 1 also, the one that we just do there. So let's take 4, 3, 2, 1. But now I'll draw it three-dimensionally. It's going to be the following. First line connects 1 to 4. Okay, second line connects 2 to 3. So it goes, but then it's forced to go under this line. Third line connects 3 to 2. So starts here. And the last line connects 4 to 1. So this is the last line. It's fine. So I've basically drawn the same 4 lines as before, but with keeping track of under crossings and over crossings. And the rule is the following. The fellow with highest priority, the one which goes above everybody else, is the line which starts at the position 1. Okay. Then next priority is position 2. Okay. So it's as if I construct this road first, then I construct the next road, okay, and then the next road and so on. And whenever I construct a road and I find a road is already existing, which I have to cross, I only have to cross it under. I cannot build a flyover. That's sort of like the rule. Okay, this is fine. The thing is clear. So first question. So if you took this picture and you sort of projected it onto a 2-dimensional thing, right? This is a, it's like flyovers and underpasses, right? It's a bunch of roads. I take a 2-dimensional picture of this, photo of this, then will it look like what we already have? A thing with 6 crossings, right? It will look like this. So that's fine. That's what it looked like as a 2-dimensional projection. Okay. So how many crossings does this picture have? It still has 6 crossings, the same 6 crossings only. Except now, by drawing a 3-dimensional picture, like we said before, every picture should give you more information than the previous thing did. Right? There's something I can get out of this, which I cannot get out of my 2-dimensional picture. Okay. So let's see what that is. It tells me something about my permutation. Any guesses? What does it tell me? Okay, in some sense, the order of the numbers is somehow hidden in this. The thing that you don't have, see, if I know that some things have only 2 crossings, or let's even take an example. So let's say I have a permutation in which I only have 1 crossing. Okay, so let's take such examples. So the simplest is with just 3 numbers. So if I take 1, 2, 3, for example, 1, 3, 2, for example, this guy is the following picture, right? 1 goes to 1, 2 and 3 cross each other. Whereas I have 2, 1, 3. It's also a permutation with only 1 crossing in which 1 and 2 cross each other and 3 goes below. Is that right? So I'm going to compare these 2 guys for the moment. So this only has 1 crossing, that also has 1 crossing, correct? So if I told you I have a permutation with 1 crossing, then you cannot figure out whether it's this guy I'm talking about or that guy I'm talking about, right? But if I told you this something more about over crossings and under crossings, then you can figure out whether I'm describing this or that picture. Okay? How? Okay. So, how will we do this? Let's do the following. We will maybe I will do it in the larger picture itself. Let's keep track for every one of these guys. Let's keep track of some numbers. Okay. So what numbers am I going to form? So for example, for this blue guy, probably should have. I have another color, right? I have green. Yes. So let me make one of them green. So I have 4 different colors. Okay. Now for each of them, I am going to write down some numbers. So first I look at this blue road. Question, how many roads does it overcross? How many roads does the blue road overcross? There are 3 lines which it overcrosses, 3 roads, right? So I write that number down. So for this guy, it's got 3 overcrossings. Next is the white line. How many lines does it overcross? Let's see, there's this green guy and the red guy. It actually overcrosses both of them, right? So it's 2. Red fellow? 1. So observe that here it's overcrossing the green line, but the other fellows it is undercrossing. So I'm not counting those. So it's 1 green, 0. It doesn't overcross anybody. It only undercrosses everyone. Okay? Total 3 plus 2 plus 1 should be total number of crossings. Right? Why? Every crossing I have only counted once. When have I counted it? Against when it overcrosses. I have only given credit to the fellow which is the one on top, right? So by doing this process, I have ensured that every crossing is only counted once in the hisab of the correct fellow, right? So the total thing is all right. So I've got 3, 2, 1 plus 0, that's 6. So total number of crossings has come out correctly. And what's absolutely astounding is the following beautiful statement, that these 4 numbers are enough to tell you what the original permutation is. Okay? See, if I tell you that the permutation has 3 crossings or 2 crossings, with that you cannot figure out what the permutation is. But if I tell you these exact numbers, I tell you the total number of over crossings, then you can figure out which permutation we are talking about. Okay? So let's see it in this case. Here, let's write out those numbers. What are those numbers here? So first I must draw the over and under correctly. So this guy goes over, this fellow goes under. Here, this fellow goes over, the next guy goes under. Okay, so let's write these 3 numbers down. So how many fellows does this overcross? Nobody. This fellow? Here? Okay, so observe already, even though the total has to be 1 in both cases, this fellow is 100 and that fellow is 010. Okay, these 2 numbers differ. Okay, and thanks. So these 2 numbers differ and they give you, in a sense, they distinguish the 2 permutations. You know what they are talking about, this guy or that guy. So this particular thing is called the code, not surprisingly. This sequence of numbers it's got a name, it's called the code. Okay, it's called the code. Okay, it's like you're encoding it in this manner and you can decode it also. If I just give you this piece of information, from that you can recover the permutation. Okay, so we'll see why in a second. But here's the question, what are the possible numbers that I can have here? For example, do you think that how big can the first number be? Can it be 6? 4? Maximum is? No, minus 1. I cannot have 4, right? Because this fellow, the question was how many roads does it overcross? Maximum available roads, there are only 3 of them. So it can only cross 3. Next fellow, maximum value it can take? Can this be 3? No, why not? Why can't it overcross 3? There are 3 roads available. The previous one, it cannot overcross the previous one. It can only undercross the previous one, right? The fellow which was already there, that it cannot overcross. It's forced to undercross it. So the only fellows it can hopefully dominate are the ones which come after it, right? So this guy can only possibly overcross these 2 lines, these 2 roads, that's all. So maximum value is 2. This number maximum is 1. This number maximum is 0. Okay? So what you're seeing here are actually the maximum possible values of these 4 numbers, 3, 2, 1 and 0. And for that, the corresponding permutation is again this guy, the one which has the maximum value of the total, right? Maximum crossings, and each of these are also, it turns out that they are maxima. Okay? So the code is the following. So more generally we can define a code. Okay, let's do it for 5 or 6, for example. So it's defined. So what is a phi code? What is a phi code? For me it's the following. It is 5 numbers, C1, C2, C3, C4, C5. Okay, it's a list of 5 numbers with the following property that C1 is some number between 0 and 4. C2 is a number between 0 and 3. In other words, C5 is 0. Okay, so take 5 numbers with the following property. The first number is anything between 0 and 4. Just choose randomly, whatever number you want between 0 and 4. Okay, next number, random number choice between 0 and 3 and so on. Okay, so give me an example. Give me some choices. Give me something for C1. Okay, C1 is 2. That's a valid choice. C2? Okay, great. You're getting unimaginative at this point. So all 2s. Why not? 0, 0? Yeah, let's do 0, at least some change from. Let's do 2, 2, 2, 0, 0. You agree this is a valid code, right? By my definition of code, see at this point, forget everything I said until now, right? So mathematicians always do this. So you have some motivation for wanting to consider, some object, but then you throw away all your original motivation and you present it as if it's some, magical thing which you suddenly thought of, at 2 a.m. or something. So anyway, here's a new definition. And if you did not know everything which came before it, this definition makes absolutely no sense. Why would anybody in the world want to even think about 5 numbers which satisfy these crazy properties? That would be and should be your first question. Okay, but now let's see why they are useful. So let's have these 5 numbers. So here's my question. Can one somehow manufacture, maybe you can even complete my question. What is the question? Can you manufacture a permutation of how many numbers? 5 numbers. Can we manufacture a permutation of 5 numbers such that the code of that permutation happens to be this 22200 that I picked? Right? So that is the question. So now let's ask that question. Find a permutation of 5 numbers of whatever, let me call it 1 to 5 such that, let's give it a name, find a permutation sigma such that the code of sigma is this random choice that you pick. How many people think one can do this? You know how you would do it? Before that, I should have said something. How many different valid codes are there? 5 codes. 5 code means just 5 such numbers, right? How many such choices can I make? Huh? Why? 5 factorial is the correct answer, yes. Why? How do you know it's 5 factorial? How many choices for C1? 5, 0 to 4. How many choices for C2? And so on. So it's 5 into 4 into 3 into 2 into 1, right? So already that's interesting. What else has cardinality 5 factorial? Which other set has 5 factorial elements? Permutations of 1 through 5, right? So we have already seen there are two sets which have the same size, which is 120. On the one hand, the set of all 5 codes. Okay, this collection has cardinality 120. The set of all permutations of 1 to 5 also has cardinality 120, right? They're both sets of the same cardinality. So already this is lending some weight to what I said earlier, that if I give you a permutation from it, I can find a code. And if you give me a code, I will also be able to decode it and find a permutation. I mean, it's not a proof, at least it's something suggestive. Just because you have 2 sets of the same cardinality, it doesn't mean you can go from here to there and back. In this case, you can. So let's try to find this permutation. Okay? So what does this code mean? What does this overcrossing mean, actually? Okay, so let's try to understand what these numbers are supposed to mean. So let's look at the first entry. It's supposed to be a 2. Okay, so what does that mean? I want 5, 1, 2, 3, 4, 5. Okay, so this first guy is supposed to go to something such that it overcrosses exactly 2 lines. Okay? So this line, I don't know where it is going. It has to go to one of these 5 choices only. But I know for sure it overcrosses exactly 2 lines. So I claim I know where it goes. Correct. Why? Right? So see, if it has to go to 3. If not, for example, it goes to 4, right? Then what will happen? Okay, let's do 3 first. So if it goes to 3, then claim is it will exactly overcross 2 lines, 2 roads. Which 2 roads will it overcross? The ones that end at 1 and 2. I don't know where these lines come from, but there are going to be 2 roads which will end at 1 and 2 for sure, right? And those lines, those roads come after this road. So for sure they will only come under it, wherever they start, correct? So if this fellow overcrosses 2 roads, that means this had better end at 3. So this is like solving some puzzle. So can also go to 4? No, it cannot go to 4, because if it went to 4, right? Then there would be roads which end at 1, 2 and 3, right? No, remember there are 5 roads which connect these 5 starting points to those 5 ending points. So from each of them there is a road which starts, and to each of them there is a road which ends. Right? That's what a permutation means, no? Matlab 3 must occur somewhere in the permutation. So something will get connected to 3. That road is guaranteed to exist. 3? Exactly. What if it's overcrossing? Why can't that happen? What if this undercrosses that road? What was my rule for constructing my roads? The first guy gets priority. So this first fellow will overcross every other road that I'm constructing in my system. Right? That is the reason why. So this is very special for the first fellow. I know it overcrosses every other road for sure. And you are also given it overcrosses exactly 2 roads, which means that this had better end at 3. Okay, it's already a very interesting puzzle solving thing. So I know that I already have discovered something about sigma. Sigma is there are 5 numbers. The first number is a 3. Okay, now let's keep going. The second road also overcrosses 2 fellows. Okay, so I've solved part of my puzzle. So let's keep going and try to solve the next bit. So this road overcrosses 2 roads. Okay, where does this road end? 5. Why? Correct. I have already figured out. Oh, sorry. That's wrong. I should let me go back to my correct answer. So 1 goes to 3. Okay, now tell me. Where does 2 go?
Should not intersect 1 and 3, so it should go somewhere below 3.
Okay, why doesn't it intersect 1 and 3?
Because of it,
One and two will go under, so it should have two.
It should have 2 roads that it overcrosses. Okay, correct. So let's look at each case in some sense, right? So if 2 goes to, let's see, if 2 goes to 2, can it happen? Can 2 go to 2? No, because then only one possible road is there which it can overcross, which is the road which leads to 1, right? Wherever that road is. That's the only possibility. So it cannot go to 2. So where it has to go is, it has to go to 4. No, because 3 is taken. Right? So we have to do this sequentially. 3 is already taken. Otherwise it could have gone to 3, you're right. Since 3 is out of contention, this fellow has to go to 4. only then these two roads will be under it. That's the only possibility, right? So the next guy is a 4. Next guy? 5, because for the same reason, there are supposed to be 2 roads which it overcrosses. 1 and 2 will surely be those 2 roads, right, if it goes to 5. It can't be anything else. Okay, next. 0, so what does that mean? This guy has to go to 1. Why can't it go to 2? It will overcross the other guy, right? So this means, and this last guy, no choice but to go to, right? So just from the sequence, the code that we want, we actually figured out what the guy is. This is all right? And so I sort of encourage you to try this out with various different choices of codes. Okay? Just play with it and see how you would do this process. Okay, now, so that's the second picture. The first picture, remember, I drew was 2-dimensional with crossings. The second picture is 3-dimensional with over and under crossings, from which we got this idea of code. And we have realized that codes and permutations are, you can go from one to the other. Okay, you can code and you can decode also. Okay, now there's yet another picture. I'm going to draw another picture. So I don't know how many people play chess. Wow, large number. Okay. What does chess have to do with permutations? Let's see. So what does a rook do in chess? It's also called elephant or something, right? I don't know. What is a rook? Elephant is rook? I don't know. Okay. So rook is, it's this piece which has only 2 directions of movement, can go vertical or horizontal on the chessboard. Okay. So here's a question. Suppose I give you a chessboard, okay, standard chessboard 8x8, 6, 7, 8. Okay, and I give you 8 rooks. 8 rooks. Okay, so I steal rooks from all chess pieces, various sets, and give you 8 rooks. And the question is, in how many different ways can you place these 8 rooks on the board such that none of them can cut any of the others, none of them can attack any of the others? Just 2 ways. Is my question clear? I give you 8 rooks and you place them on the chessboard however you want, but the requirement is that no 2 of these rooks should be able to attack each other. Diagonally, you can place all of them diagonally, correct? Why were there only 2 ways? 2 diagonals. Acha, you are only thinking of the 2 diagonals. Are there other ways? Huh? 2 into 8 factorial. Why?
8 factorial in 1 diagonal.
No, 1 diagonal is only one way, right? No, I didn't understand. Why? How did you get a diagonal is only one method? No, they're all the same rooks. They're all the same rooks. Yeah. Sorry, they're all the same white rooks if you wish. There's no need to be in the same diagonal, correct? How else can you place them so they cannot cut?
For every of the x coordinates, you just choose a y coordinate and you can't choose the same for the next one. So you just get 8, 7, so on. So it happens.
Okay, so let's draw 8 cross 8 is too difficult to draw. Let me draw 4 cross 4. So I take a 4 cross 4 chessboard and I place 4 rooks. Okay, let's start with that. So where will you place the rooks? You don't need to place them diagonally, right? So I place one of them here, place one of them here. Can any of them intersect any of the others? Cut any of the others? Right? Nothing can attack anybody else, right? Why did we do, how did we do this? We ensured that in every row and column, there is exactly 1. There's exactly 1 rook, right? The first column, there's 1, second, third, fourth. Rows, exactly 1. Okay, in each row and each column, there should only be 1. That's exactly what it means, right? They can only move horizontally or vertically. Just ensure that when you place a rook somewhere, its row and its column don't have any other rooks, right? And how many ways are there of doing this? 4 factorial. Why? It's actually like a permutation as follows. Why is this question is secretly a permutation? Okay, why? In the first, so let's do it one by one. In the first row, so I'm going to do the following. I'm going to write rows and columns down. Okay, in the first row, which column did I place my rook in? Second column. In my second row, I placed it in the fourth. In the third row, first. In the fourth row, okay. So this is just my permutation. My permutation is 2, 4, 1, 3 if you wish. So I ignore the rows now. Okay, forget this. So anyway, rows will always, I will list them in the same order, 1, 2, 3, 4. So if I give you the permutation 2, 4, 1, 3, it means you place second column, then fourth column, then first column, then third column, in that order. If I change the permutation, you place it accordingly. So there are exactly 4 factorial ways of doing this, one for each permutation. Likewise, on the standard chessboard, there are 8 factorial ways of placing rooks. Okay? Okay, good. So this is going to be our third picture. So we drew a 2-dimensional picture and a 3-dimensional picture. Now we'll draw what I'll call the rook diagram of a permutation. Okay, so this is third way of understanding permutations. Let's draw its rook diagram. No, there are 4 factorial ways of doing it. So why don't you give me a permutation of 4 numbers? Just give me a permutation. For, 1, 2, 3 and 4, just permute it any way you like and tell me something. 2, 3, 2, 3, 1, 4. Okay, so let's take this permutation 2, 3, 1, 4. Okay, that's going to be my permutation. Let me draw its rook diagram for you. So its rook diagram is just the following. Okay, so I see the first number 2. So I place my rook in the second column of the first row. So I go row by row. Okay, I'll do first row first, second row next, third row, fourth row. Okay, I will go row by row, or if you wish, you put those position numbers on top. So remember we were doing this, right? We were writing the position numbers. So you see, okay, if I see position number 1, 2, matlab row number 1, column number 2. Okay, next I see a 3. So in the second row, I'll place my rook here. 1, I place it here. 4, I place it there. Is that fine? That's actually it's among the simplest representations of permutation. I just think of it as some rooks on a chessboard, okay, of the appropriate size. Okay, now, okay, so let's try to match up all our pictures at this point. So 2, 3, 1, 4. Let's also draw our other picture, our 2-dimensional picture. Okay, so 2, 3, 1, 4 is what? 1 goes to 2, 2 goes to 3. 3 goes to 1, but I have to do under crossing, and 4 goes to itself. Correct? This is what 2, 3, 1, 4 is. Okay? Now, what is its code? Okay, very good. So let's see. First guy only meets one fellow overcrossing. Second guy overcrosses one fellow. Third and fourth don't overcross anybody. So the code of this permutation is 1100. Correct? Okay, now I claim that at this moment it's not visible to us, but the code is actually hidden in the rook diagram. Okay, so here's my rook diagram. I claim that we will try to discover the code inside the rook diagram. Okay, So let's see if we can find the code. So we do it in 2 steps. Okay, so what are the 2 steps? First, we look at every dot and I'm going to put an X in before, in all the boxes before every dot. So this dot, anything to its left, I'll put an X. This dot, I'll put 3 X's. Okay, this dot I cannot put X's because it's already in the first column. So is it clear what I did? Step 1, put a cross in all the boxes before a dot, before my rook. Okay? Okay, next, we now look at these dots and the dots now do the following. They don't like anybody in their own columns. Okay? So each dot, below it in its column. Okay? So each dot is going to do the following. It's going to sort of look below it, see whoever is in its same column and kill all of them. Okay? So that's step 2. So who all get killed? This cross goes away because this dot doesn't like this fellow, right? Now this dot doesn't like anybody in its column below it. See, above is okay. Okay, I'm not going to touch these 2 crosses. I'm not going to touch. I mean, this fellow is not going to destroy them. It will only destroy fellows below it. Okay, and this dot doesn't like this fellow because it's below it in its column. Okay, fine. Step 2 is clear. Step 1, you first put some candidates, put some crosses. Step 2, you destroy some of these fellows. Okay. Now you see who you are left with. How many are we left with? How many in the first column, first row? There's 1 guy in the first row, 1 guy in the second row, and nobody in the other. Okay. So this is the procedure. Let's just check on another example to see that this is not a coincidence. Okay. Let's do one more. So let me take 3, 1, 4, 2. So here's another example. Let's draw its, what shall we draw, rook diagram or, so okay, let's draw this diagram first. 1 goes to 3, 2 goes to 1, 3 goes to 4, 4 goes to 2. Okay, so I drew my 3-dimensional diagram. Now, what's my code? First guy overcrosses two fellows. 0 doesn't overcross anybody. This overcrosses 1 fellow, 0. So the code of this permutation is 2, 0, 1, 0. Okay. Now let's draw the rook diagram. So rook diagram. Three, 1, 4, 2. Okay. Step 1, we first fill all crosses. We just fill it with crosses to the left of every dot. So remember, if you think about it, you'll see you'll always put 6 crosses because there'll be 3 crosses before the guy in the 4th. There'll be 2 before this fellow. There'll always be 1 before this fellow. Right? No matter where they are, you'll always put 3 in one row, 2 in another row, and 1 in another row. Total 6 you'll always put. Here also we did that, 1 plus 2 plus 3. Okay, but how many get destroyed is not in our hands. That depends on where those dots are, right? So let's see how many get destroyed now. So this dot doesn't like fellows below it. These dots survive. This dot doesn't like this fellow. Okay, so how many dots survive? 2, 0, 1, 0. Okay, and it's not too hard to prove this, that it will always be the case that these overcrossings and undercrossings are really, it sort of gets translated into this particular aspect in the rook diagram. Okay? Okay, good. Now, okay, so what I want to do also is to understand the reverse process. Okay, sorry, was there a question? Somebody? Okay, so let's also go in reverse. Okay, by which I mean, if I give you the code, then can you directly construct the Rook diagram from it? So slowly we are building up sometimes a bewildering number of ways of thinking about a permutation. So we should just keep track of what these are. So on the one hand, we just talked about permutations as usual. Now, from the permutation, I talked about its code. Okay, given a permutation, we know how to get its Rook diagram. Okay, and given a Rook diagram, I know how to get a permutation also, right? These two are, of course, more or less the same thing. From a permutation, we know how to get a code. Given the code also, we said how to find the permutation, right? Just requires a little bit work, but algorithmically, we kind of understand how to, if I give you some code, you can actually write down using undercrossing, overcrossing, what the permutation is. Okay, and now let's complete this triangle. Given the Rook diagram, I told you how to get the code by sort of putting those crosses and destroying some of the crosses. Now let's go in reverse. If I give you the code, can you directly draw the Rook diagram? See, what you can do is if I give you the code, you can first find the permutation. And then from that permutation, you can draw the diagram. That's always available as a method. But let's say I want to do it directly. I don't want to do all this. I don't want to first find this and so on. So I tell you a code, I just quickly want you to draw the diagram for me. Okay. So again, that's again very easy. So it's the following. So let's just do it again by example. So code. So let me give you some code. So let's pick some. So it's supposed to be 4 numbers. This fellow is at most 3. This is, let's put some numbers. 3 for this guy. This is at most 2, 1. So 3, 1, 1, 0, for example. So let me take this code. Okay, so I just pick some random code. It's a valid code because first entry is at most 3, second is at most 2. From this code, let's directly construct its Rook diagram. So the first thing says, this is a 3. Means what? How many crosses? 3 crosses should be there in the first row. 3 surviving crosses. But in the first row, every cross will survive because a cross cannot get destroyed in the first row, right? The dot from above only can shoot it down. But there's no dot above it. So there are 3 crosses in the first row, that is guaranteed. Okay, good. So therefore, where is the dot? It's after the cross, of course, right? So that's the dot. So I know first row already. Let's look at next guy. 1 means what? There's only 1 cross in the second row. Where should it be? We'll just start from the beginning. Just start filling from the beginning. Okay? So you always start from the left end and fill. So there's only 1. So this is the dot. Okay? Then next guy is a 1 again. There should be only 1 surviving cross in the third row. Again, I'll start from the beginning and put it. This is my cross. Where's my dot? Why not in the second? Right? There's already a dot there. So of course, dots don't like anybody below them. So it's this. Right? And finally, it's a 0. Where's the dot? Because that's the only available place. Right? Okay? So this is one thing that we did. Let's tweak this a little bit and see if we can figure it out. So instead of suppose I had that. Now let's 3, 0, 1, 0. Okay? So 3 is still 3, done. In the second row, I don't have any cross. Okay? So how will I do that? No crosses, so I just put a dot there. Okay? In the next guy, I have 1 cross. I should start here ideally, but can I put a cross here? No, why? This fellow will shoot it down, right? So where can I put next? That's all right? That I will put. And then where's my dot? And finally, where's my dot? So you just see which is available, that's all, right? So you see what we did in the second guy, right? So this is this sort of algorithm that we are just doing. So this is sometimes what's called the greedy algorithm, right? All such algorithms are what you call the greedy algorithms, which is you always start from the beginning and you keep filling as many crosses as you're supposed to fill, subject to the constraints. There is only one constraint here, that if you find a dot above you, you cannot put a cross there. Okay? So you keep filling. If that square is not good, fill in the next available square. Right? That's what greediness means. Just fill in the next available place and keep going. Okay? So this is actually a very, very quick algorithm, which is, if you give the code, you can just fill these crosses out in no time. Okay? So that gives you the, that tells you how to find the permutation or the root diagram directly from the code itself. Okay? So we sort of have several different ways of doing this. Okay. So let me say yet another thing about permutations. Okay. So why are permutations important? We said sorting is one of its most important applications. It occurs when we want to sort things. Now, there is this the following situation. So I've got a train at a platform, but it so happens that, when the train came in, the sleeper coaches were not arranged, S1, S2, S3 and so on, but instead permuted in some fashion. Okay, so let's say what they were, 5, 4, 6, 2, 3, 1. So let's imagine the coaches came in like this. Okay, the train is attempting to, that's the track, it's moving in that direction. Now, of course, that's no good. We want it to be arranged in the correct order, right, before it actually gets to the station. So this is something that, by the way, they often do in railways and so on. So there's something called a shunting yard, right? So I don't know if you've heard this term. There's a shunting yard where, these coaches are taken and then sort of assembled in the correct order and sent to the station. So let's imagine we have the following thing available to us in order to shunt this or put it back into the correct order. We've got a track. Okay, so what is the track? The track is the following. So this is my shunting track. Okay, this is the original track. It's coming in like that. Okay, I'm allowed to sort of move it to my yard, and once it's in the yard, I can move it coach by coach to the yard, and then I can move coaches back out. Okay, so there are these two tracks. One track which takes me from here into the shunting yard, and I can, by the way, I can move them piece by piece. I don't need to move the whole train in and so on. So let's see how a thing like this can be helpful to permute something. Okay, how will you use only this much apparatus to permute the coaches into the correct order? So let's do the following. I will take coach number 1, push it in, and push it out. Okay, there are only two things I can do: input and output. Input means move this guy into the shunting track. Okay, so first I do an input operation, and then I immediately do an output operation, which means I move this one back out. So this one is now here. Okay, then the next coach is coach number 3. Okay, I will again input this guy. So I did input, then I did output again. Okay, so 1 came in and went out. Then input, 3 is now sitting in the shunting yard. What should I do next? I input 2 again, right? So I sent 3 there, and then I also sent 2 there. So where will the 2 sit? Because it comes after the 3. Okay, now what can I do? So I do 2 inputs. So I output 2, which means the 2 goes away from here. 3. Okay, I'm already in business. 1, 2, and 3 are in the correct order. Okay, let's see if I can successfully do that to the rest. Okay, input, I move the 6 in. Input, I move the 4 in. Output, I move the 4 out. Okay, so 6 came in, 4 came in, but 4 moves out. Okay, last 2 steps. Input the 5 and output the 5. Finally, output the 6. That's the 4, right? So, is this clear what we did here? Okay? Sorry, I missed something. Uh, Here, correct. Correct. There should be 6 outputs, 1, 2, 3, 4, 5, 6. All right. So this is, this is a very restrictive sort of sorting. So this kind of thing is called stack sorting. Okay. So are stacks something that you've encountered in data structures? Does anyone know what a stack is? What? Last in, first out. Okay. What does that mean? Okay. So a stack is a data structure which has got things called a push and a pop operation. So a stack is exactly this shunting yard. Just I push something into it, I push one more guy into it, then I have to pull that guy out first. I must pop that first out. Okay, like you saw what happened here, right? So 3 came in, 2 came in, but 2 has to come out first. So this shunting yard is exactly a model for the stack. So this kind of sorting is called stack sorting, meaning I'm only allowing myself, I'm tying my hands behind my back because I'm not allowing the full power of, I can't do exchange sort. I cannot just happily interchange any two and bring them in order and so on. I'm giving myself some extra conditions, some restrictions. I'm saying I only have a stack with me. That's all I'm allowed to use. Okay. But using that, you've got to tell me how you will, what will be your instructions, sorting instructions, which will sort my original thing. Okay. So let's do the following. Here's exercise. Let's take all the 6 permutations of 1, 2, and 3. Okay. And let's stack sort them. Let's write out input output instructions to stack sort every one of these guys. So let's start with 1, 2, 3. Okay, so imagine, if you wish, if this helps you, imagine that you've got this. So if 1, 2, 3 comes in, what should I do? First 3 goes in, 2 goes in, 3 goes in, 2 goes in, 1 goes in. 3 fellows have to go in. Output all 3. So then 1 will go out, 2 will go out, 3 will go out. So train is correctly right? 3 inputs followed by 3 outputs. What if it's the other way around? Input, output, input, output, input, output. Right? Because 1 comes in, 1 goes out. 2 comes in, 2 goes out. 3 comes in. Okay? Very good. So let's do this for 2, 1, 3. 3 goes in. Right? Let's do it for 2, 3, 1. Input, output, 1 come. Input, input, output, output. Right? Okay? 3, 1, 2. Input, input, output, output, input, output. Okay? Very good. What's left? I only have 5 permutations here. Very good. What's the sequence? What? Input, okay. Input, input. Sorry, tell me, one person tell me what comes next. Okay, what would you do if you had to do it? No reverse and all. I'm not allowing you all that. Whatever comes in can only go out like that. Not possible. Is everyone convinced it's not possible? Let's try, right? How would we do it? Okay, 2 comes in, that's input. 3 also comes in. So what does the stack look like at that point? So I have 1, 3, 2. This fellow comes in. 2 is at the bottom. 3 has come and sat on top of it. What would you ideally want to do? 1. Right? Why are we doing all this? Because 1 has to come to its correct position. Right? 1 is what we are keeping our focus on. So the 1 finally came in. We are happy. So we'll push the 1 out. Right? We are feeling like it's getting done. But now we run into trouble. What happened here? The 1 came out. What should you now attempt to extricate next? 2. But can I get it out? No, because it's stuck below the 3, right? I cannot get the 2 out because there is a 3 stuck on top of it. It's stuck under the 3, okay? So I cannot do this. This is not possible, okay? And it's not so surprising, like I said, see, this is sorting with more restrictions. You're only allowing yourself a stack, and a stack is a less powerful object than, you know, the sorts of things you're doing with exchange sort and so on. Okay, but more generally, not all permutations can be stack sorted. First moral of the story. Second question, what is it about a permutation that prevents it from being stack sortable? So suppose I give you a permutation of 10 numbers. Can you somehow figure out from this analysis, maybe 10 is too much, let's say 5 numbers. Say I have this set of 5 numbers, okay? I'm going to try and stack sort it in my mind. How will I do it? Keep pushing, pushing, pushing. As soon as I see the 1, I'm happy. I get the 1 in and I get the 1 out, right? And then I start looking at 2. What will I do with the 2 and so on, right? Now, when will this fail? Okay, when will it be impossible to do this? So the answer is the following. Suppose as I scan my list of numbers, let's even imagine it's larger, right? Even it's a longer list of numbers. Suppose the following happens. There are 3 numbers which occur in this sequence, which such that the smallest of them comes first. Okay, so there are 3 numbers. Look at the numbers 1, 3 and 2. Of them, 1 is the smallest. The smallest fellow comes first. The largest of the 3 comes next. Somewhere in that, it doesn't need to come after it, right? And then after some time, the medium of the 3 comes here, okay? So what I'm saying is, when I have a sequence, so let's give an example of this. Let's say 10 numbers, okay? So at some point I see the number 3, okay? After some time I see the number 8, and after some time I see the number 5. Okay, so I'm giving you an example of a permutation of 10 numbers, okay? 10, 100, doesn't matter, whatever, any number of numbers. But that sequence, that permutation that I have has a following property that first somewhere 3 occurs, after some time 8 comes, after a few more places 5 comes. I claim that this guy can never be stack sorted. Okay? Why not? Because how would we, suppose it were stack sortable, what should have happened? See, 3 is the smallest of the 3 numbers, right? So if anything, during this process of stack sorting, what should have happened? At some point the stack, you know, I would want to push the 3 out. The 3 should enter the stack and it should exit the stack, right? So how will I get the 3 into the stack? The only way I can get the 3 into the stack is 5 and 8 should have already come into the stack, right? So at the instant when I'm trying to pop 3 out of the stack, I know for sure that 5 and 8 are both inside the stack, right? They have to be there just by the nature of the process. Now, I successfully remove the 3 out, but then at that point, after the 3, let's say there's 4, etc. to be done, you know, there's more process, but then at some point the 5 will have to be removed, right? As I keep going. Now, the 5 cannot be removed because the 8 is on top of it. Okay, it's the same logic. So 1, 2, 3 are 3 consecutive numbers, but that's not required. If I have 3 numbers, the smallest fellow comes first, the largest guy happens to occur next, and then the medium guy occurs, then such permutations cannot be stack sorted. Okay, so these guys are called, so let me just use, so you say that a permutation is, so we use the word avoids small, large, medium. Okay, you say it avoids SLM. SLM is a pattern. Okay, small, large, medium. You say that the permutation avoids this pattern means you cannot find 3 such numbers. 3 such numbers don't occur in that permutation at all. Okay, so permutation avoids SLM if, let me just be informal, if this doesn't happen. Okay, what is this? This kind of thing. It doesn't contain 3 numbers such that the smallest comes first, the largest next, and the medium next. Okay, so let us look at examples of okay. So how do you construct examples of permutations which don't have this small, large, medium pattern? Okay, so that's going to be my next question. So let's do this for a permutation of 8 numbers. So now my question is, of 8 numbers. So is this definition clear? What it means? It should not have this kind of pattern, that's all. Okay? But now this is a tough question what I'm asking you. I'm saying I want you to manufacture a permutation of 1 through 8 such that small, large, medium never occurs. So there's one obvious answer. Some easy answers are there. Put them all in ascending order, right? 1, 2, 3, 4, 5, 6, 7, 8. I can put them descending order also. 8, 7, 6, 5, 4, 3, 2, 1 is also an example. Because small, large, medium. So that's never going to happen. So those are 2 obvious examples. But the question is, can you construct more examples? Can you find others? Okay. So for example, I want such a permutation 1, 2, 3, 4, 5, 6, 7, 8. Let me tell you that I want such a something which doesn't have something which avoids SLM, in which the 8 occurs in the, let's say, 3rd place. So I want an example in which 8 is there. Okay? So let's try to understand what that means. So there are 3 places to the left of 8, and how many to the right of 8? 4 places. So there are totally 7 numbers which I should fill here. 3 to the left, 4 to the right. Where can one, okay, sorry, say that again. 5, 6, 7, 8. Will that always, sorry, there you're giving an example. Okay. There's in fact more. The numbers 5, 6, and 7, they can occur in various orders, but those 3 guys will occupy these boxes. Okay. The first observation to make is, these 3 fellows are where the 5, 6, and 7 will occur in some order. And 1, 2, 3, 4 are all going to occupy these 4 spots, possibly in some order. Okay. Why should that be true? It has to avoid small, large, medium, right? Remember, 8 is the largest of all the fellows. So that is one candidate, large guy. So what can't I have? I can't have a small fellow here and a medium fellow there, right? Which means, see, if I pick any number, that is, if I pick 1, 2, 3, any of those numbers, anything other than 5, 6, 7, if it comes here, if that is, for example, 1, 2, 3, or 4, then of course there is a medium fellow available for me to put on the other side, right? Small, large, medium, I will be able to put. So all the medium fellows, I should make them come to this side, and the large, small fellows should go to the other side. So avoiding SLM is actually this, it seems like a strange property if you say it like that, but it's actually this very, very beautiful recursive structure. It says, just focus on where the largest number is. So if you know where 8 is, then that splits it into 2 parts, okay? And 5, 6, 7 will come here, and those guys will be there, okay? So I'm going to just construct this as follows. 8 is there, and then there's a sort of some fellows to the left, some fellows to the right. So let's keep going. 5, 6, 7. Now, first observation, this guy, or let's do 1, 2, 3, 4, this fellow also doesn't have a small, large, medium in it. Is that right? That is, of these 4 fellows also, I shouldn't be able to find a small, large, medium, no? If I could find SLM within these 4, then of course it is an SLM in the full list. Likewise, among these 3 also I cannot find an SLM. Here there are only 3, but I shouldn't be able to arrange them as small, large, medium. Right? 5, 7, 6, for example, is not allowed, because that's small, large, medium. Right? So I know that. So this is the recursive structure. Once you figure out this bit, each of these is a permutation of the appropriate numbers, which again avoids SLM. Okay? Which means I keep going like this. Of these 4 numbers, focus on the number 4. Okay? You put it somewhere, wherever you want. So let's put 4 somewhere. So this is the next step. I'll put 4 here. Okay? Automatically I know what these numbers are. What is this number? Only one option, 1. What are those 2 numbers? 2 and 3 in some order. I don't know yet. Okay? That's something to do. Let's come here. I know these 3 are 5, 6 and 7. I'll put 7 wherever I want. Okay? I'll put 7 here, for example. Then there's nothing to the right of 7. What are these 2 numbers? 5 and 6 in some order. Okay? So this is the recursive structure. Now let's come here. I have 3 and 2. I can put 3 wherever I want. And 2 is fixed. 2 has no choice. Likewise here, I put 6 somewhere and 5 goes here. Okay? This is how you construct a permutation which avoids this SLM pattern. Okay? You keep doing it recursively. Okay? And one encodes what we just now did in the following manner. So I have 8. Okay? Let's keep track of what's on the left and what's on the right. On the left, what's the maximum fellow? 7. On the right, 4. Okay, now 7 again splits it into 2 parts. Right, things to the left of 7 and things to the right of 7. Okay, what's to the right of 7? Nothing. So I'll put an empty there. Okay, this is an empty set, or maybe we'll just leave it empty. Okay, what's to the left of 7? The maximum guy is a 6. Okay, 6 again splits it into 2 parts. One of those 2 parts is empty. This part is empty. That's a 5. Okay, let's go on to the other side. So 4. What are the 2 pieces? Right guy maximum is a 1. Left fellow? Maximum fellow is a 3. That splits it into 2 pieces. Where does the 2 occur? On the right side. Okay, what did I just construct? Okay, what kind of tree? It's a binary tree, right? Binary tree ka matlab, what's a binary tree? Every parent has 2 children, at most 2 children. See, if it has exactly 2, it's called a complete binary tree. This is not complete, that's all. Okay, some of the children could be empty, that's the only thing. But the beauty of this is that, the numbers that occur in it are in a very special form, that the root, the parent, has values which are greater than all its children. Okay, every parent is more than all its children. 4, because remember that was the maximum guy in that block. So this fellow, the parent beats all the children. Second property, the children on the right the other way around. The children on the left beat the children on the right. At any parent node, take any node, the left children are all bigger than the right children. Okay, and the parent is bigger than everybody. And that's a property that's recursively true in this tree. Okay, the way it's written out. And so in a sense, how many SLM avoiding permutations can one construct? The answer is it's actually equal to the number of binary trees. So you just try drawing binary trees of all the different binary trees. Okay, so if you observe how many SLM avoiding permutations of 3 numbers were there? There are only 5 of them, right? Let's draw the binary trees for all of these guys. Okay, let's just draw the same pattern that we drew. So the first thing is there are exactly 5 binary trees with 3 nodes. Okay, how do we get them? So for example, what's the tree for this fellow? 3 to 1. 3 is the top. The left is 2, 1. Right? So this is this binary tree. So I will erase the numbers after I draw the tree itself. So that's my binary tree. Okay, then next guy 3 to 1. What does 3 to 1 look like? 3 is the maximum. Okay, 3 splits it into 2 children. There's no child on the left. Child on the right is 2, 1. 2 is the maximum. Again splits into 2 parts, but 1 is on the right. Okay, so this is this binary tree. So I'm trying to draw all binary trees on 3 vertices. Okay, that's this. 2, 1, 3, likewise, what will this look like? 3, everybody is on the left, but there's a 2 and a 1 is on the right. Right? So it's this tree. And so on. So you keep going like that. Okay, so try doing this. So you'll find that these two will give you the other two possibilities. So there are only 5 ways of doing it, and those are exactly the equal to the number of SLM avoiding permutations. Okay? Okay, so now one last thing about all of this, which just ties everything together in some sense, which is, again, let's do it by example. So I'm just going to finish with this example maybe. So we constructed this SLM. This is, remember, it's an SLM avoiding permutation. Okay, and as I said before, SLM avoiding is the same as stack sortable. Right? So what are the instructions? Sorting instructions. Let's see if we know if we can figure out the sorting instructions for this. Okay. What's the first sorting instruction? No. By sorting instruction, I mean input-output sequence. If I put it into a stack and put it back out, what will I do? What sequence should I do? First, I input my 1 and output the 1, right? So input-output. I input the 4, I input the 2, output the 2, input 3, output 3, output 4. Right? After a while, it's nice. You can actually just keep it in your head and do it if it's not too hard. Okay, then the 8 comes in. That fellow will be input, but he will stay inside for a long time. 7 will also stay inside for a long time. Input, and output all of them. Correct? So that's my input-output sequence, which will stack sort this particular guy. Correct? Okay. Now, so like I said, this is going to be the grand finale, which will tie everything up. Let's also write the rook diagram. Okay, now 8 cross 8. I guess I bargained for more than I imagined. Let's do chessboard, therefore. So the rook diagram of this guy, 1, 2, 7, okay, so what is the rook diagram? 5, 6, 7, right? 5. Where is the 5? 1, 2, 3, 4, 5. 6, 7, 8, 3, there, right? 3, okay, 3, 2, 4, 1, correct? That's my rook diagram. Now, let's also figure out the code of this permutation. So, you recall what that entails. I need to figure out where my crosses are. Okay, so first step, let's put all the crosses that did I get everything? Right? I just put crosses to the left of all the dots. Okay, now we'll destroy the crosses. Which one should we get rid of? So let's look. There's nothing below this fellow. There's this one guy below this. 2 guys below this. Nothing here. 1 below this. 1 below this. Correct? So that's my diagram. Okay, and remember that's the code. What are these crosses finally? They're supposed to tell you what the code of the permutation is. And what does the code mean? Code, remember, was what are the maximum values? This guy is maximum 7, right? It's also clear from this diagram because maximum 7 crosses you can have, right? 6 and so on. So what I'm going to do is, see, they're kind of all going to fit into this triangle of the chessboard. Okay, the crosses will always be only in this triangle. Is that right? Is that clear? The crosses will always only be on the top half of the chessboard. Because, like we said, code, right? This fellow maximum 7, maximum 6, maximum 5, and so on. So they're kind of actually in the top half. Okay, so let me just make this a little darker. Anything interesting you notice about the crosses? I mean, this pattern of crosses. So this is not a random permutation. Remember, this is a special permutation. SLM avoiding permutation or stack sortable permutation. There's something extra special about it. And that extra special property somehow should be visible when you also draw this diagram here. Okay. Anything special about this? All crosses will always be above diagonal in any permutation. That is all right. But when I gave you examples of those permutations, those configurations of crosses, there was something you saw in those examples which you are not seeing here. Huh? There will never be any crosses in the diagonal.
There is no space between the.
Brilliant, absolutely. So notice that when I gave you those examples, those crosses, sometimes there were gaps between the crosses. Why? Because some dot on top killed all those crosses, right? So if you remember, there were examples where, there was a cross, then nothing, and then a cross afterwards. That never happens here. That is the special property test. The crosses are all contiguous. They are, gapless. There are no gaps. That's exactly the property. That's what it means, okay? So stack sortable permutations are also the same as, Rook diagrams in which the crosses occur without gaps. Okay? And when they occur without gaps, they will also occur in descending order, meaning, see, there are 4 here, 4, 4, 4, 2, 1, 1, it will always be descending. Okay? So that is a property. And now for the final thing, what else is, see, this is a diagram of a stack sortable permutation. Now, stack sortable permutation can also be thought of as the instructions. Right, here's another way of encoding a stack sortable permutation. You just tell me what is the machine instruction. What is the I's and the O's? If you tell me that, I know what my permutation is, right? I can just actually do it and figure it out. Now, final thing, this sequence of I's and O's, the machine instruction, is also hiding in this diagram. I claim that if you stare extremely hard, you will be able to find this sequence of I's and O's somewhere in this diagram. Any inspired guesses of where? Okay, so let me do the following. I will draw the boundary of the crosses alone. So we have to focus only on the crosses. So it forms a certain region, right? Okay, and then I'll also reach the ends. So this is the pink line that I drew is going from this bottom to that guy, but tracing the boundary of my region of crosses, yes.
The line is overlapping with the right line is output, input. Then when it is slanted, then output, then it is output, input. It's like slanted lines to vertical.
Absolutely. Vertical and horizontal, yes, that's what you mean. So if you look at this boundary, every time it's vertical, it goes up. Think of it as input. Okay, if it's horizontal, output. Input, input, output, input, output. Are we good so far? I, O, I, O, I, O, O, another output. then 4 I's, right? So observe I, and 4 O's. Okay? So the machine instruction is actually hidden in this diagram, finally. It's actually that boundary of the crosses that gives you this. Okay? Okay, I think I will stop with this. I think it's been an overload of permutations for one day. But I should just point out some references, I think, for a lot of this stuff. I mean, for many things, surprisingly, Wikipedia is a great place to start on many topics on mathematics. So a lot of these sorts of things this is what's called pattern avoiding permutations. So if you sort of search for pattern avoidance on Wikipedia, there's a Wikipedia article on pattern avoidance, and I would highly recommend just starting there and following up on any of those additional references that you may feel like looking up. It's a very, very deep subject actually. I mean, it goes on all the way to the frontiers of current research in mathematics. And in fact, a lot of this very interesting, some of the seminal results have actually been by Indian mathematicians working in Chennai. So there's an Indian connection to a lot of this as well. So I mean, if you sort of have a lot of free time, and there is also a lot of programming stuff that you can do, including recursive stuff like binary trees and things like that, which come up when you study these guys. Okay, so start there, and if you have any questions, feel free to write to me. That's another thing I should have said. This is my email address. It's svis@imsc.res.it. Okay, so I'll stop here, and if there are any questions, of course, I'm happy to take them.